how'd the block get in the water? Yeah, so what else could have happened? I didn't explain it very well, but what else could have happened? Right, so heat also goes from the block to the air. Heat, energy, goes from the block to the air. Okay. If you can remember, energy moves from high temperature to low temperature, you're good to go. So what's going to happen to the temperature of the block? It's going to go down. What's going to happen to the temperature of the water? It's going to go up. What about the air around this system here? Like, I mean, if this was happening here, right, the air over here probably wouldn't be affected. But the air around this system here, what would happen to the air immediately around it? Probably increase in temperature, right? Okay. So, that's conservation of energy. Usually I don't have to spend a lot of time on it because you experience this stuff in real life. Things feel cold, things feel hot, but now you just have to understand what the direction is. It's always from warmer to colder, every single time, okay? Now, this thing is a supersaturated solution of sodium acetate. What the heck is that? Well, you can actually take sodium acetate's a white compound, like crystalline compound. You can dissolve sodium acetate, a massive amount of sodium acetate in a little bit of water. It's extremely soluble. And you can essentially force the water, so there's water in here, to hold more sodium acetate than it thinks it can. In other words, if you have a beaker and you add salt to it and you stir it up and it dissolves, and you add more salt, stir it up, it dissolves more. Eventually, if you keep adding salt, what's going to happen? What do you think? It's not going to dissolve. This stuff, you can add a lot of it, and eventually the water won't dissolve it anymore. Does anyone know how do you get something to dissolve if it won't dissolve? So you stir it for hours, it won't dissolve. How do you get that extra solute to dissolve? You do this all the time. Well, maybe you don't do it all the time, but some people do it all the time in the winter. Something people drink when they're cold or they have a lack of heat. Hot chocolate. It's hot. Why is it hot? Because you're lacking heat. Because you're cold. No, something else. Because it tastes good. Think of the chemistry. Why do we heat it up? To dissolve the chocolate stuff, whatever it is, powder or liquid or whatever it is. Who uses the powder? Okay. At the end, when you're done drinking the hot chocolate, at the very bottom, what do you sometimes see? Like a chocolate sludge, right? Sometimes? What is that? That's this. Huh? That chocolate sludge was dissolved. When you're done, it's not dissolved anymore because the hot chocolate cooled off. See, hot liquids can dissolve more than cold liquids. So, I'm trying to give you some examples, and you're probably still confused. Here's the deal. You take this white, there's white stuff in here, and I didn't make this, but what they did was they heat this up, and all of this will dissolve. Let it cool to room temperature, and it'll stay dissolved. There's that little coin thing in there that I flipped and I bent. What that does is it shakes the particles. So all the particles are dissolved. And when I bend that thing, in there, a little metal coin, that students always think when I do that, that's like some sort of chemical thing. All it is physically kind of moving the particles. I could shake it. That would probably do it too. But this works better. I don't have a great reason why. Probably because it's in there and it's actually interacting with the particles a little better than just shaking it. But all it's doing is agitating the particles, and then they form crystals, and then it spreads. Once the crystals start, it's like a chain reaction. They all start becoming undissolved, precipitate. So this is just dissolving and then precipitating, dissolving and precipitating. All I have to do is put this in a beaker and boil the water. All this will dissolve. And then let it cool down to room temp, and then it looks clear again. And then I'll just twist that thing, and then it becomes undissolved. And this sodium acetate, when it becomes a precipitate, a solid, it comes out of solution, like the sludge in the hot chocolate. When this comes out of solution, it gives off massive amount of heat. It's exothermic. It's a physical change because it's just dissolving and then becoming not dissolved. That's all it is. So I just kind of went through all types of chemistry that we're going to learn this year, so you might be confused, that's fine. But it's just like hot chocolate. If it cools down, it's going to become undissolved. So eventually this gives off heat, that's the confusing part, but when it cools down after I twist that, it's all precipitate. If I wanted to get that sludge in the hot chocolate to dissolve again, I would have to heat it up. So if I heat this up again, it'll all dissolve again. So, and it'll reverse the process. So this is physical change, a supersaturated solution. We'll talk more about that down the road. All right, so conservation of energy, we are moving on past that. Let's define, let's see, hold on, I don't want to forget something here. Let's define the word heat. We're talking about heat, let's define it. What is heat? Anybody have a good definition of heat? Well, it's a form of what? Energy. Basically, the way we define it is heat is energy that is transferred from a system with a higher temperature to a system with a lower temperature. Let's talk about phase changes. Let's talk about heat and phase changes. Meaning solid, liquid, gas. If we are going from a solid to a liquid to a gas, so let's say we have ice, right? We can just use an example. We have ice, we have water, and we have water vapor. So let's say you were holding that ice cube still. Why did it melt? Shane. So was the ice cube absorbing heat? Okay. So let's say Shane, you were able to take that water in your hand and boil it. So you can just think about it and just create all this heat in your hand and boil the water. Kind of cool, maybe scary. Would the water be absorbing heat to boil? So to go from a solid to a liquid, from a liquid to a gas, Shane's telling me it absorbs energy, the whole process. Who agrees with him? Monique, you agree? So in order to go from a solid to a liquid to a gas, this absorbs heat. That's called an endothermic process. Put it in parentheses here, endothermic. Endothermic process. When heat is absorbed, it's called endothermic. So going from solid to liquid to gas, heat has to be absorbed. But what does it have to do with the transfer of energy? It's got to be coming, the heat has to come from somewhere, and in the ice's case, it's coming from your hand. If we wanted to boil the water, we'd have to take the water and then heat it up on a hot plate or a burner. You know, our hand's not going to do it, all right, or a stove or something. What if we're going the other way? We flip it. Gas to liquid to solid. If we have to gain energy to go from a solid to liquid, from a liquid to a gas, what's the opposite then? We have to lose heat. So we lose heat. And what's that called when something gives off heat? Exothermic. Exothermic. Let's talk about why this happens. Why this happens. So I'm out of room here. I'm just going to put it here. Why does it have to gain heat? Why does it have to lose heat to change phase? Let's talk about the first one here. Absorbing heat to change phase. What does the heat do to the ice that allows it to turn into water? I said it yesterday. I don't know if anybody picked up on it.
It speeds up the molecules.
Okay, good. When heat is absorbed, the particles move faster, and then it does one more very important thing. How does a solid turn to a liquid? Something else has to happen. Shane. The what? Don't use the word bond. Give me something else, like gravity. I used gravity as an analogy for this earlier this year. So it keeps particles close together, but they don't actually touch. It's like an imaginary, this word.
Attraction?
Yep. Force of attraction, right. When heat is absorbed, the particles move faster and weaken the forces of attraction. And sometimes break the forces. So that's why phase changes occur. And then when, this is the one here, when we're going solid to liquid, you're weakening the solid particles' attraction. That's why they're separating a little bit and moving around a little. Now they're water, the liquid. And then, to go from liquid to gas, particles go from being this close to really spread out. So from here to here, you're actually breaking forces. From solid to liquid, you're just weakening them. From liquid to gas, you're completely breaking them apart from each other. And then to do the opposite has to occur. You got to cool the gas down so the particles move closer together and move around less to become liquid. Then you lose even more heat. The particles start to kind of stand still, maybe vibrate, but they're not moving so much. So it's the exact opposite. This one, this what we wrote, this is more important to be able to explain. All right, this is just the opposite, so I'm not going to really write that as well. But that's an important concept. So this conservation of energy stuff is really important to understand. Energy is transferred, and when that's transferred, what happens? Okay. Besides the fact you can memorize the definition, energy is not created or destroyed. Yeah, whatever. Anyone can memorize that, but can you explain what's that mean and what's going on? So this is kind of what's going on, all right, with energy. So now, somebody explain. Well, you know what? Okay, yeah, we'll talk about that. No. Let's do this first. Sorry. I'm getting confused in my head what I want to talk about. I got 3 things I want to talk about here. Remember the word entropy. What does it mean? Entropy. Hannah. Chaos or disorder. Good. Write this down. All systems in nature tend to progress towards high entropy and low energy. This word for word is on the regents all the time. Which of the following occurs in nature? And then you'll have 4 choices. All systems in nature tend to progress towards, and then this is the right answer. But then they'll say high entropy, high energy. Low entropy, low energy. Low, high. So they'll flip the words around. So this is a good time for me to bring this up because we know what this means. We just started talking about energy. In general, as things progress through time, this is what happens. This is what happens. I use people as an example. What? Think of a baby. and think of someone who's 100. And think of them as they progress through their life in relation to those two words. Let's talk about entropy. As you go from birth to 100 years old, think of you as a person, your body. What happens to you as you get old? As you progress? What happens? What does that have to do with entropy? No? You got nothing? Think of your skin. Wrinkles. Yes. What are wrinkles caused by? Anyone know? Well, you have collagen and all types of other things in your skin that literally break down over time and they don't come back. So that's why people who have wrinkles can't get rid of them unless they do what? Yeah, like some sort of weird surgery, chemicals, but naturally your skin becomes literally chaotic. Okay, if you were to like zoom in with a microscope and look at like your skin now, and then your skin when you are 80 years old, the 80-year-old skin is going to look like it's in shambles. The moral of the story is, as people age, they fall apart. That's chaotic. That's disorder. Okay? High entropy. Think of a car. As cars get older, what do? They break down, they rust, they fall apart. Think of any machine. As things progress, they fall apart. High entropy. Who moves faster? Slade now or Slade when he's 100?
Slade when he's 100.
Not true. When you are younger, you tend to have more energy. As you get older, I'm starting to feel this now. For the first time in my life. I guess I'm reaching some sort of point where I just get tired at night. That never happened. So when I was younger, I had energy. I could run around for days. As you get older, your energy just dissipates. So in general, think of a tree. Think of anything, okay, that exists in our world. Both of these are true. Things break down over time. A lot of chaos. Things don't have as much energy. They move slower. Okay. Ever been behind an old person driving? Do they drive fast? Maybe some, but most of them drive real slow. Low energy, okay? Probably because they don't know what's going on and they have a lot of entropy in their brain, okay? I'll be old. It'll happen to me too. I'll get mine. Trust me for making these jokes. But the concept is high entropy, low energy. I'll go over that with you about 100 times this year because it's kind of a random question, but it makes a little sense. Okay, next thing I want to talk about before we get out of here is temperature. And that's what your homework is on. Temperature. Does anyone know the definition of the word temperature? I'll assume that's a no. It's the measure of the average kinetic energy of the particles in a system. The measure of the average kinetic energy of the particles in a system. We just started talking about energy, so we should talk about temperature and what it means. It's the measure of the average kinetic energy. What is kinetic energy? This is energy due to motion, right? I think a lot of you already probably know that. I hope so. Potential energy is stored, kinetic is moving. So energy due to motion. So particles are moving around. Temperatures, thermometers, take the average kinetic energy. So some are moving faster, some are moving slower. Temperature is a measure of the average. There's two scales we use. We use Celsius and Kelvin. Celsius and Kelvin. Here's what your homework is going to be on. Converting between Celsius and Kelvin. That's a good skill that you need to have. So here's the formula. It's on the back of your reference table. It's degrees Celsius plus 273 equals Kelvin. this is the equation you're going to need to convert between Celsius and Kelvin. So, for example, this room, it's not showing, but let's say this room is 21 degrees Celsius. What would that be in Kelvin? And Kelvin is capital K, by the way. What would that be in Kelvin? We plug the 21 in here, so it would be 21 plus 273, and that would equal 294 Kelvin. So I'm basically out of time, but I wanted at least to get to the beginning of temperature. Practice on the worksheet using this, converting. We'll talk more about the scales tomorrow and what they mean. All right, we don't use Fahrenheit.